Okay, we're going to take a look at differentiating something other than e to a power and integrating something other than natural log. So, you should remember that when you're dealing with a base of e, the derivative of e to the x is e to the x. But consider what happens when you're not dealing with, say, an e to a power. Suppose you had, say, 2 to the x. Well, you could go ahead and rewrite that as e to the natural log of 2, all raised to the x, which when you have an exponent raised to an exponent, you could rewrite it as an e to the natural log of 2 times x. You need to remember that e raised to a natural log, the e and the natural log undo each other, leaving you only with the 2. That's the property that we're using to help us out here. So for the most part, you can just start with, say, 2 to a power, and you could rewrite it as e to this. And that's what this formula right here is saying. Once you would have it written as e to a power, then you could go ahead and easily take your derivative. We're not asked to do that here, but we will anyways. If you did want to take your derivative, remember e to a power is still e to that power times the derivative of your exponent. The derivative of your exponent is just x times something is what your exponent is. Derivative of x times anything is just that anything, so it's really times the natural log of 2, which if you did simplify that would be your natural log of your 2. Remember, your e to the natural log of 2 is just 2, still raised to the x, so it's 2 to the x here. That's what it is for your derivative of, say, 2 to the x. But that's really, for the most part of the lesson later here. So let's go ahead and take a look at this problem here. We're dealing with carbon life, or carbon half 14, which is a half-life situation. We're starting out with 1 gram. We know the half-life is this. Well, your 1 gram is what you put in front, 1. Well, multiplying by 1 doesn't mean change anything. It's half-life, so we're going to have a half. Now, the exponent you have really needs to be the number of half-lives. If one half-life is 5,715, the number of half-lives is really your total time divided by this. And so that's what we're saying here with your exponent. Well, we're wondering how much is going to be left after 10,000 years. So really all you want to do is put in 10,000 for your time. This is your calculator ready form. You type it into your calculator to get the decimal approximation. And then you'd also want to go ahead and remember your units. So you get 3/10 of a gram, approximately. Well, to refresh your memory on logarithms, we know how to take the derivative of a natural log. You know that the derivative of a natural log of x is just 1 over x. But if you're not given a natural log, and say you were given, say, the log base 2 of x and have to take the derivative, all you'd have to do is just use your change of base formula. And since we know how to take derivatives of natural logs, change it into natural logs, we could go the natural log of our x over the natural log of our base, which is 2, which, if you wanted, you could write it as 1 over the natural log of 2 times then just the natural log of an x. For the most part, that's what we're saying up here. So when you have log base 2 of x, you could rewrite it in this form. That's what this rule is saying up here, just using properties of logarithms. By the way, if it was in this form here, then you could easily go ahead and take your derivative. Taking your derivative wouldn't be too bad. This is just a number times this, so that's going to stay there. Multiply it by then the derivative of your natural log, which you know is 1 over x, which I would then write as a 1 over an x times my natural log of 2. Now you could write it as 1 over natural log of x times 2, or sorry, I said that wrong. Natural log of 2 multiplied by x. But for clarification purposes, I'm going to put the x in front so there's no misunderstanding. Is the x hanging out with the 2, or is it the natural log of 2 all multiplied by x? Having it this way makes it easy to differentiate between the two. Now the rest of this page is just to refresh your memory on logarithms. Here's your logarithmic form, here's your exponential form. It's basically your definition of a logarithm. Remembering what's after your log always has to be positive. And then down below are your properties of logarithms again. So here we're not asked to solve or differentiate or integrate, you're just asked to solve. So it just goes back to your pre-calc. So I'm going to just go ahead and apply a log to both sides. I like to use a common log or a natural log because my calculator does that. It doesn't do a log base 3. So remember, when you have an exponent after a log, you could put that in front of your log. Now you just have x times something. So to get x by itself, you just divide. This is your calculator ready form. If you needed the decimal approximation, you could just type that into your calculator. Now on the right-hand side, we're not solving an exponential equation like we were here on the left. We're solving a logarithmic equation. So we need to undo our log. So that's what I refer to as the Tarzan. I'm going to take the 2, swing it over, and that hits the -4 up as your exponent. When you do that, the log drops. So basically, you're just applying the definition of a logarithm that we talked about on the previous page. Well, that negative exponent, you should remember, puts the 2 to the 4 in the bottom. So you just get 1/16. Now, here, this is kind of what we were talking about before on the previous page, or a couple of previous slides. This is saying when you have a to the u, to take your derivative, you go natural log of a times a to that u times the derivative of your exponent, du dx. Now you could go through all the steps we did on the very first slide to do that, or you could just use this formula. On the third slide, we talked about taking the derivative of a log other than base natural log, and we ended up with something that looks similar to this, which was the 1 over natural log of a times the 1 over u, and in this case, it's all multiplied by the derivative of u. That's the chain rule. So you can just use those formulas, or you can go back and convert it to an e for this one and convert it to a natural log for this one and go through all that process. Does not make a difference. So here we need to go ahead and differentiate this. So we know it's going to be a 2 to the x, but then you got to multiply it by the natural log of your 2 using the formula from the previous page. This one here would say, well, we'd still have to have our natural log of 2 times our initial function, but then since it's not just a normal x up here, times the derivative of the exponent, which is just a 3. So I'm going to just rewrite that and put the 3 in front, natural log of 2, and then still my original function. Over here, we have a logarithm, but it's not a natural log, so I need to use a change of base formula to write it as a natural log. So I'll take natural log of the top over the natural log of my base, which isn't written, so it's assumed to be base 10. So now, all I have to do is work this out. Now, that's just a number. That's going to continue to hang out here. So now I got to do the derivative of this. Derivative of a natural log says it's 1 over what was after your log, so it means the cosine of x is in the bottom. But then you got to multiply it by the derivative of the inside. The inside is cosine. Derivative of cosine is negative sine. Well, that simplifies a little bit. Sine over cosine is tangent. So it's really a negative tangent times your 1 over your natural log of 10.